It's a very powerful way of looking at. The mathematicians have given this orthonormal representation long, long ago, but the credit goes to Wozencraft, at MIT, somewhere around 1950s, to look at the signal as a set of numbers in vector space. Although mathematics was all there, but first time it was done, and then this concept was used extensively by communication theory people after Wozencraft created it in this manner somewhere around 1950s. As late as that, although mathematics probably is much, much older than that. So all the communication books which you open, any good book, not all books, but any good book, will always, the authors will give credit to Wozencraft. And he just passed away very recently, and actually his student is Jacobs, I.S. Jacobs. You know who this I.S. Jacobs is? The CDMA Systems, which is a big company which Qualcomm founder and owner is I.S. Jacobs, who is a student of Wozencraft, and he has become a multi-billionaire after setting up the Qualcomm. And he happened to be a student and then did his PhD at Cornell. So just last year he is given some $10 billion to Cornell as a gift to the alma mater. So these are the kinds of stalwarts who worked on these conceptual things. Then there is we have done this also in 101. For example, if you have a sinusoid, which is a general sinusoid like f of t into cosine omega ct plus theta t, which has an amplitude f of t and a phase equal to theta t, both are time varying. You only studied probably theta being a constant, but there is no need for theta to be constant. Theta can be time varying. In fact, in communication, if theta t happen to be time varying, we call it phase modulation. And if f is time varying, amplitude is time varying, we call it amplitude modulation. And you can have combined modulation, both amplitude and phase, in which case like PSK, FSK, these are names you will hear in day-to-day almost, right? And the PSK signal is what is used for your communication, or MPSK and so on and so forth. So these are terminologies arising out of the simplification, where what you choose for f of t and what you choose for theta of t. So basically the function is a very simple function, a sinusoidal function with a carrier frequency omega c with an amplitude time varying as well as phase also time varying. This can be represented written down as equal to f of t cosine omega ct cos theta t minus, or maybe let me put minus here so that I can put a plus here, is f of t sin omega ct sin theta t. Simple trigonometric expression. If you combine this and this and this and this, so this is something like fct cosine omega ct plus FST sin omega ct. Many communication signals fall under this category, where this is called the carrier frequency, right? When you say your cell phone has a operates at frequency like 950 gigahertz or 1.8 gigahertz or 2 gigahertz or 4 gigahertz or 5 gigahertz, that means the electromagnetic energy is transmitted, radiated at those carrier frequencies. There is no information on the carrier frequency per se, except that you use it for purpose of communication. Information regarding the signal is only built into this and this. These are random signals which carry information from one point to another point. So there is not much importance for this term and this term in terms of omega c. What is important is this and this. This I can represent as equal to a f wiggle t e to the power of j omega c t, a real part. Right? Which is nothing but, if ft is a complex term here, and if this complex term is equal to fct minus, right? When you multiply this by this, you and take the real part of this, is nothing but this. Okay? There is no information in this. The only information is in this f cap t, the complex. We call this f cap t complex envelope. Because it is, if one of the terms is 0, then obviously this will be only just real, this will also be just real. Some problem? Okay. So the name of this is called the complex envelope. So the complex envelope as a complex function, you know what a complex function is or not? We started the complex variable theory in this, just now in mathematics I was told. So you know that means there is a real part and a imaginary part, and the complex variable theory tells you this is some number and this is some real number, but the number can be time functions in general. So that is what we are talking about, is a complex envelope. It's a function is a complex function. So this is a complex function representation of a real signal which is given by this. Since all the information contained in that signal is contained in this, because this contains both amplitude as well as the phase of this function here, then this is good enough for me to operate upon the complex envelope. I don't have to worry about this portion because there is no information. So we will come back to, when we come to system theory, we will come back to, if you have a system which will deal with such complicated signals like this as the input to the system, I don't have to go on carrying these cosines and sines and all this in terms of analysis. I can forget about the sine portion, cosine portion, and deal only with this and see the response due to this for the black box, and from there I can immediately write down what is the response due to the original variation in terms of including cosines and sines. What is the advantage of this way of looking at the signals in terms of a complex signal in place of two separate real signals. I look at this as a single signal, which is a complex signal. And ft modulus of this, as you can see, is nothing but square of this plus square of this, which is square root. Right? Modulus of f cap t is nothing but square root of fc square t plus fs square t. And theta, which is the angle of f cap t, is nothing but tan inverse fs by ft. Okay? So many times it is convenient for you to look at such signals in terms of analysis, not in terms of all the complicated format, in terms of only just the envelope of it. And this envelope is a complex envelope. Sometime later part of the course, we will come back to this equation, and Fc and Fs are related to each other in some manner, and if Fs happen to be the so-called, we'll just hear the word only now, Hilbert transform. If this is a Hilbert transform of this function, what is the Hilbert transform will come to know as we go along. I want to do today itself, but unfortunately I didn't have the complex variable theory background, so I am postponing it. So someday we will come back to this, and if these are related by Hilbert transforms, then it turns out that this complex function has some beautiful properties, and we use this Hilbert transforms quite frequently in